Hey Python bros, what's up? Today I want to continue our conversation around A/B testing. We're going to talk about how to handle a continuous measure such as playtime and how to test whether our improvements are significant. Stay tuned. Let's go ahead and load some libraries. We'll start with pandas and then NumPy for operations. Bam! Now we need to load our data. In today's data frame, we are going to be loading some D0 Playtime, which means this is the amount of gameplay our users did when they downloaded the app. It looks something like this. We have an ID, we have our cohort, our test group, and then our playtime. When we see that our test group is 1, that means we implemented a change that we're hoping improves the product and leads our players to play more. 0 is our base version of the game, and we're going to be comparing the two variants with one another. We're looking for statistical significance in order to eliminate noise and make sure that we are really improving the product. A pro tip, go ahead and remove all players that have 0 or no D0 playtime. Why? We're gonna assume that we don't have any game-breaking bugs that would lead more players to not be able to play our game. By removing players with no gameplay, we're cleaning our data and are able to compare playtime in a coherent manner. You can be even more aggressive and remove gameplay sessions under 5 minutes. However, it depends on our sample size. In our case, we have a relatively small sample size of 10,000 players split across two variants, which usually isn't enough to get a good normal distribution. But we're gonna test that later. Let's go ahead and clean our dataset. We're gonna go ahead and just specify that we're looking for playtime values that are over 0. We've removed 200 rows. Fair enough. Your playtime once you install a game is one of the biggest indicator whether you like the game and whether you're gonna retain and possibly monetize. That's why we're looking at this metric so closely. Let's start off with doing a power test to make sure that we have enough samples. If we look at the chart here, whether we have a large sample size or not will determine our next step and ultimately the test we're gonna do. Let's call this section sample size and power. Our group 1 is equal to our clean data frame filtered for just the control group. Bam! In this case, we just need the playtime, so let's slice our data frame and get our playtime values. We can repeat this process for our variant group. Let's call it group 2 and make sure that our test group is equal to 1. Bam! So far so good. I am not gonna go into details on what a power test does, but I strongly advise you to familiarize yourself with the approach, concept, and assumptions. It's gonna make your life a lot easier going forward. The first step we need to do is get the average playtime of our first group. Let's create a variable called group1 mean, call group1, and calculate the mean. Bam! 35 minutes. Let's go ahead and repeat the same process for group 2. Bam! Let's see which one is higher. Group 1 has 35 minutes. Group 2 has 33 minutes. If I was looking at these two values, I wouldn't really bother with Group 2. Our game time did not improve. But let's say our other metrics for Group 2 are much better than Group 1, and this is the only metric where we have concerns. Let's validate whether these concerns are valid or if they can be attributed to statistical noise. In order to proceed, we need to calculate a metric called a pooled standard deviation. Bear with me, please. It's a long calculation, but generally we're getting the two variances of the groups, mashing them together and creating a baseline. Sort of. Our pooled standard deviation is calculated on the base of the sample size of our group 1. Since this is a sample, we're going to be taking a -1 out of it, times the variance of group 1. We also need to add the same calculation for group 2. Bam. Let's put this in brackets. And we need to divide by the total sample size minus 2. We're essentially creating a proportion. Since this isn't even remotely long enough or complicated enough, we actually take the square root. Why? It has to do with standard deviation and variance and their relationship. Our pooled standard deviation is an error. Amazing. I missed a letter. Okay, our pooled standard deviation is 42 minutes. Oh wow, that's quite high. We need to calculate our effect size next. This is basically group 1 mean minus group 2 mean divided by the pooled standard deviation. This means that we are trying to detect something like 4.3% difference. This next part is gonna not make immediate sense, but just trust me when I say our alpha is going to be 0.05 and our power will be 0.8. Those are standard industry benchmarks. Our ratio is our sample size of group 2 divided by the sample size of group 1. Bam. All that's left is to actually do our power test. We're gonna go ahead and import a independent power test. Let's go ahead and call our power test. Let's calculate the needed sample size per group. We're calling our power analysis dot. We are solving for power. Our effect size is equal to our effect size. Our power is equal to power. Our alpha is equal to alpha. And ratio is ratio. It works. We'd need 8,377 sample sizes per variant to detect properly the difference that we're seeing in our A/B tests. We're currently almost a third under that, so we don't have enough samples. We can go ahead and calculate the observed power of our sample. Let's call our power analysis again. We are solving for power. Our effect size is again the same. Our alpha and ratio are also the same. However, instead of passing power, we're gonna go ahead and pass the sample size of our group 1. Whoops. I had a typo. So our current power is somewhere around 62%. That means that only in 6 out of 10 cases we can be sure that the findings we're seeing are statistically significant. And that's not good enough. Let's do a recap. We have a non-discrete metric. We have playtime, which is continuous. We tested whether we have a large enough sample size. The answer is no. Now we need to check whether our data is normally distributed. We wrote a lot of code, so let's take a step back and use some graphs. Let's go ahead and import Seaborn as SNS, and let's import matplotlib as POT. Another trick you can do is write %matplotlib notebook. Bam. I like to do SNS set style, and let's do white grid. Like, this is all cosmetic. We're gonna use a plot called KDE plot. It goes something like this: sns.kde plot. Let's pass group 1. Let's give it a color. Let's do blue. Our label is gonna be group 1. Let's do fill for true so we have no gaps. Our normal distribution is false. And let's set some alpha. Let's take this and also do it for group 2. Let's change the color to orange. Our plot title is A/B test distributions. Our X is playtime. Our Y is distribution. Let's add a legend and POT.show. Bam. Does this look like a normal distribution to you? Yeah, me neither. Now let's prove it. We're gonna be using SciPy stats, and we're gonna import our Kolmogorov-Smirnov test and also norm. Bam. Let's do stat comma p equal to ks test. Let's pass group 1, norm, and then for arguments we're gonna pass group 1 mean and group 1 standard deviation. Let's put this in brackets, close out our test, bam. Okay, let's check if p is more than 0.05, and it is not. So we don't have a normal distribution in our group 1. Let's do the same for group 2. Nope, not normal either. We confirmed our intuition, we don't have normal distributions. Final stretch. Our data isn't normally distributed, which means we're gonna do a Mann-Whitney test. Oh yeah! Okay, from SciPy, import stats, and that's where we're gonna get our Mann-Whitney test from. Bam! Our test returns a U statistic and a p-value. Let's call our stats library and then Mann-Whitney U. We're gonna pass group 1, group 2, both of them in our raw format. And let's do a two-sided test. Bam. Our p-value is again extremely small. Bam. Our p-value is under 0.05, which means there is a statistically significant difference between the two groups. we reject the null hypothesis. So what does that mean? If we go back to our graph, we can see that group 2 has a higher peak in the lower playtime values. Group 1 has slightly more players that played between 30 and 100 minutes, and we don't really care about the tails here. That means that in the A/B test we conducted, our variant, which is group 2, had a negative impact on playtime, and that's concerning. We need to really evaluate the risks of pushing this change into production. If monetization and retention metrics are up, then we can compromise on playtime, but it's generally a very bad idea to push changes that reduce playtime of your players. That's the bread and butter of your game. And that's pretty much it. We looked at a specific continuous measure that we had to use a Mann-Whitney test on, and we managed to prove that the change we're looking to introduce into our game, product, or app negatively impacts the time our users spend with it. That's already a reason to consider not rolling this feature until we improve it and are sure it actually benefits our product/app. I'd like to thank you for watching this whole video. I sincerely hope you managed to learn something new. I truly hope you managed to understand a facet of A/B testing slightly better. If you have questions, let me know in the comments. If this video helped you, do me a favor, like the video, subscribe to the channel, leave me a comment. It helps me grow my audience. Thank you very much. I hope you stay awesome, and until next time. Oh yeah!